Welcome to this lecture series in group theory. Last time we discussed what is Z mod and Z and an addition on it and a multiplication on it, which I'm calling the algebra on Z mod and Z. So we saw that the algebra on this guy almost made it a field, except that not every non-zero element here has a multiplicative inverse. But if n were a prime, then we saw that the obstruction to it being a field vanishes. And hence, for every prime, we have that Z mod PZ is a field. In particular, Z mod 2Z is a field which we typically denote by this symbol F2, and usually when we express this as a set, we just write this particular set 0, 1. So we don't put any fancy bars or anything. We, from the context, will understand that this 1 refers not to our usual 1 of integers, and this 0 doesn't refer to the usual 0 of integers. These are just two symbols which behave in the following way: 0 plus 1 is 1, 0 plus 0 is 0, whatever, 1 plus 0 is 1, 1 plus 1 is 0, and similarly multiplication laws. So we know what those laws are, we discussed them, and with that let us proceed. So let me start with a puzzle which will orient us or anchor us to the following concepts. So fix a collection of subsets of this particular set where script C has size n plus 1. So we have this n element set. We collect some subsets of it, call that collection script C, and assume that the collection that we have has at least or exactly n plus 1 things in it. Okay. For example, if n is equal to 4, then this set becomes equal to that. And here we have a collection of subsets of this particular set, where this has size 1 more than the size of this set. Okay. The claim or the challenge is that to show that there is a subset of the family, meaning a sub-collection of the given family of subsets, with the property that every element of the original set lies in an even number of elements of this subfamily or sub-collection. So the statement is a little complicated, but if you think about it, you will understand what it is trying to say. Let's see what the statement is saying in this particular example. So here I have this sub-collection and it satisfies the hypothesis of the statement. So let's see, can we find a subfamily of script C which has this property that everything here is contained in an even number of elements of the subfamily? Clearly, the family C itself doesn't have that property because the element 1 lies in 3 of them, not an even number of them, but 3 of them. So clearly we have to, if at all, we have to drop some members of this family, and maybe we will retain some elements which confirm to this proposition. And indeed, if you forget about these two, if you drop these two, then this new subfamily or this subfamily has that property, because 1 lies in 2 of these guys, 2 lies in 2 of these guys, 3 lies in none of them, and none means 0, and which is an even number. So 1 lied in an even number of them, 2 lied in an even number of them, 3 lied in an even number of them, 4 also lies in an even number of them. So that's clear. So at least in this example, we have verified this statement, but we want a general proof. And it's not very simple, right? It's a purely set theoretic question. But it's not so simple, right? What to do? Today, we will see a proof of it using linear algebra. We will endow power set. We will endow the power set of any non-empty set with a vector space structure over F2. And then this statement will just fall out of that what should I say? Will just fall out of that fact and just basic linear algebra. So let this puzzle anchor us to what follows. All right. So before we move ahead, let us recall that if X is any set and F is any field, then this set, what is this set? This set is the set of all the maps from X to F. I don't know how to write it. So it's all maps, all the maps from X to F. Okay. And this is just an alternate notation. This thing over here is just an alternate notation for this guy. So when we write f to the power n, this is something we must be very familiar with. We write this as all tuples, all the n tuples, where each xi is from f, right? And we know how to add things here and how to scale things here. But this object is really, if you think about it, it is nothing but the set of all the maps from the n element set 1 up to n to the field f. How? Every tuple you can think of as a function from this to that, right? What is this function? It takes 1 to x1, 2 to x2, and so on, n to xn, that function. So every tuple is really a function. Tuple is not a fundamental mathematical object. Everything in mathematics we try or we want to express in the language of sets, functions, and relations. So what is a tuple? A tuple is a function. So instead of writing f to the power 1 up to n, we just abbreviate and write f to the n. So that's the meaning of this notation, but we are more familiar with the tuple notation here. Whatever. So anyway, so that was just a digression. Right. So we have this set of all the maps from x to f, and how do we make it a vector space? This you must have seen in linear algebra. You add functions pointwise. So if f and g are two functions from x to f, then f plus g is also a function from x to f, which is defined how? It takes little x to fx plus gx, just a pointwise addition. And if lambda is any scalar, lambda is any element of the field, and f is any such function from x to f, then you can define a new function lambda f, which sends little x to lambda times fx. So pointwise scaling and pointwise addition, the most natural operations that you can think of on this guy, make it a vector space over the field f. Right, so this is your usual basic linear algebra. All right, and if x is a finite set, then what is the dimension of this space? The dimension of this space is mod x. Why is that? Because consider these functions delta x. For each x in the set capital X, you can define this function delta x, which is defined how? Which takes little y to 1 if x equals y and 0 otherwise. And you can easily prove that this is a basis. This is a basis. Let me write it as a set. Okay. So the size of this set is clearly mod x. And yeah, so therefore the dimension of this guy is mod x. So here, of course, I'm assuming that x is a finite set because I'm not assuming you're familiar with linear algebra beyond finite dimensional vector spaces. So even though in this discussion we didn't really need x to be finite, but just assume that x is finite for simplicity. Okay, so let's proceed. Right, so we will talk about symmetric difference. Suppose A and B are two sets, then the symmetric difference of them is defined as the following set. The notation is A, then you make a delta and then a B, and it is the collection of those elements which are in A but not in B, or which are in, let me just write it as follows. It's basically A set minus B union B set minus A. So what is this notation now? What does this mean? This is those things which are in A but not in B. And what is this? This is those things which are in B but not in A. And you take the union and you can easily see that this is also equal to A union B, and you take away the intersection. Right? But if you wanted to draw a picture, if this is A and that is B, then the symmetric difference is the shaded region, the things which are in A but not in B, and the things which are in B but not in A. Very simple concept. So here is a small definition. For each subset A of x, we define an element of f2 to the x. Again, recall what is f2 to the x? F2 to the x is the set of all the maps from x to F2, and this is a vector space over F2. Right, so we define this guy as an element of this as what? As follows. 1a of x is 1 if x in A and 0 otherwise. Okay? It's a very simple definition. We are just capturing the set A in a different way. Instead of looking at it just as a bland subset of x, we are looking at it as a function from x into F2. Here you could have said it for any field, like really the field F2 is not so important here, but let's keep it F2 for a certain reason, because otherwise there will be some unnecessary confusion that might be caused. So we are defining the indicator function of A. It is called the indicator function of A. It's a nicely chosen name. It's just indicating if a given input lies in A or not. Okay, it's a very simple definition, but the point of this definition is the following lemma, if you will. Once you pick two different subsets of X, and it is completely fine if you choose the empty set also, the indicator function of the empty set is nothing but the function which takes the value 0 everywhere. Okay, so once you pick two different subsets of X, we want to say that this equation holds. This addition we defined already. This addition is as addition happens in this vector space, right? Just pointwise addition. We are saying once you add these two indicator functions, you get another indicator function which is coming from the symmetric difference, so to say. And the proof is very simple. It's nothing. What is this value for any x? This is equal to 1ax plus 1bx. If x lies in both a and b, then this also gives a 1 and that also gives a 1, and hence you get 0, which is the same thing you get from the right hand side. If x lies in both a and b, then x doesn't lie here. If x lies in both a and b, then it doesn't lie in the symmetric difference, because you subtract or take out the intersection precisely. So it matches. If x is in both a and b, then this value matches with the corresponding value for this. So let me not write that. If x lies only in a but not in b, if x lies only in a and not in b, then this will give you a 1. For that particular x, the right side will output a 1, and this will also output a 1, because this guy will output a 0 and this guy will output a 1. So you can just easily check. You can make three cases, you can make three cases. First is that x is lying in both a and b, then it matches. X lies only in a, then it matches. X lies only in b, then also it matches. And if x lies outside both a and b, that also has to be checked. If x lies outside both a and b, then this also fires a 0 and that also fires a 0. And the right side also fires a 0, because the right side is in particular contained in A union B. So whatever, you can just make 4 cases and check. It's a triviality. And now I want to say something. I want to claim that fix any non-empty set and pick 3 subsets of X. Then the first one is a triviality, that the symmetric difference has commutativity property. Right? This is a triviality, just check. This is also a triviality. If you take the symmetric difference with the empty set, you don't disturb the set. That is a trivial check. This is also a triviality. Asymmetric difference A is empty, because you can just look at this expression and see. But the last one, this is a nightmare. This is unclear. The associativity of symmetric difference is not so clear, and if you try to prove it, you can do it. It's just a matter of some hard work, if you will. In fact, you can explicitly write down the expression of it. If you make the Venn diagram, if you just draw the diagram corresponding to it, A, B, C, and then you try to shade it, you will see what this set is, and that will also immediately show you that this equality holds. But it will take some time to prove it formally. Drawing a diagram is one thing, giving a formal proof is another. So it's not so clear why this equation holds, but we will show very shortly that this equation does hold using a different technique. We will not directly prove it. We will not indulge in proving it by using set theoretic logic, etc. We will make use of this fact. So let's get there. So we can reinterpret the power set of X as this particular object. Now, what is power set? Recall, power set of X is all subsets of X, including the empty set and the full set. Here, whatever I'm going to say doesn't really depend on X being finite, but for simplicity, you can take X to be finite. So power set of X is just all subsets of X. Also, you must know already that the size of the power set of X is 2 to the power mod X if X is finite. Otherwise, power set is also infinite. Okay, so what we are going to do is we are going to define natural functions from power set to this set, or this vector space if you will, and conversely from that vector space to power set. So I've drawn this diagrammatically here. We want to define a phi and a psi in some meaningful way. We ultimately want them to be inverses of each other. But for the moment, forget about this clause. Suppose I ask you to define such a function. Suppose I ask you to define a phi from power set to this guy. What can you do? Like some nice function, not the constant function 0 or anything, some nice function. So if you just think about it, the most natural choice would be the following. Phi of a subset A of X is just the indicator of that set, right? The most natural function from power set to F2 to the X. Similarly, what is a most natural function from this to that? Well, if you pick something here, it's a function from X into F2, right? But F2 as a set is just this thing. So you have a function from X into that guy. Some of the elements of X are going to 1 and the others are going to 0. So let's say these are going to 1 and everything else is going to 0. So in some sense, psi A is captured by this part or its complement, but let's say just this part. But what is this part? It is just the pre-image of 1, yeah, right? Because this is precisely those things which map to 1. So this part is just the pre-image of 1 under this function. So psi is just nothing but, we define psi as psi of a function f is just the pre-image of 1 under that function. To be very, very clear, this is nothing but all the things in X which map to 1 under f. But again, you have to remember this 1 refers to the 1 of this guy. It's not your usual integer 1 or anything. So these are two natural functions that you can define from power set to this guy and from this guy to the power set. What is their composite? What if you compose the two? Well, I've already written what is the composite because I'm saying that these two things are inverses of each other. So this is the identity, but it should be clear anyway. Let us formally prove it. Here is the proof. Psi of phi of A is by definition psi of 1A. But what is the pre-image of 1 under 1A? The indicator of A fires a 1 if it is inputted something from A and 0 otherwise. But to be very formal, I mean to write down every little thing, this is nothing but those X in A such that this happens, which is precisely A. That's the definition of the indicator function. So we see that if you compose psi with phi, you get the identity on the power set. And similarly, it's an exercise that if you compose this way, you get the identity on the vector space. Okay, so there is a natural bijection. There is a natural bijection between this object and that object. And further, we are saying, and this we have kind of already said in the previous slide, that the symmetric difference maps to the sum. So phi takes the symmetric difference and maps it to phi A plus phi B. This is nothing but phi A plus phi B. And that we have already said in the previous slide because phi of asymmetric difference B is the indicator of asymmetric difference B, which is 1a plus 1b as we saw in the previous slide. Okay, so we have shown that there is a natural bijection which preserves, or not preserves, but which kind of reinterprets the symmetric difference operation as a much simpler looking operation. And as a corollary of this fact, we now can show that the symmetric difference is associative. Meaning what? Meaning this. So why is that? Well, so here is the proof. We have asymmetric difference. So want to show that this is the case where A, B, C are arbitrary subsets of X. Want to show this, but this is equivalent to show, or enough to show that if you apply phi to them, you get the same thing. Here we are only assuming, or sorry, we are only using the injectivity of phi, right? Showing this is equal to this is equivalent to showing this equation because phi is injective. Phi is a bijection, that's fine, but in particular it is injective. So if you can show that phi gives the same output on two different inputs, the two inputs must be the same. But now what is this? This is equivalent to showing what? This is equivalent to showing that the indicator of the left side is equal to the indicator of the right side. But what is this indicator? This indicator is 1a plus the indicator of B symmetric difference C. Right? We just observed, or in the previous slide we observed that this holds. So the indicator of A symmetric difference something is the indicator of A plus the indicator of something, and similarly for the right side. So we just want to show this, but we again apply the symmetric difference business, the indicator function and the symmetric difference business. So this thing is same as asking for this being true. But this is obvious. We are saying that functions add associatively in a vector space, in particular this vector space, which they do, right? In any vector space, addition is associative. So whatever, like it's a triviality now. Here it was a nightmare, this thing, but here it's a triviality. So it is indeed true. Great. Let's move on. So now, having seen a natural bijection between the power set and f2 to the x, we can pull back the vector space structure from f2 to the x to the power set. So what I'm saying is a very general thing. Suppose we have some vector space V and we have some set S and we have some bijection between them. Let me use phi. This is a vector space while this is just some ordinary set, and we have some bijection between them. Then we can borrow the vector space structure or exploit the vector space structure on V to give S a vector space structure, right? Just define addition on S so that it tallies with the addition on V under phi. To be very precise, what you would do is define an addition on S, meaning a function of this sort. How do you define it? Well, you first consult with V, which you do by phi cross phi. So you wanted to add two things here. What you do is you first pass to the vector space V by applying this function, which is not a mysterious function. It just is applying phi slot wise. So if you feed it a comma b, it will output phi a comma phi b. Right? It is just applying phi slot wise. So this is also a bijection. Okay. So you go here. Now here you can add. This was a vector space. So here you can add. So yeah, you add things. You get something in V. And now you come back. Now you come back to S by applying phi inverse. You wanted to add two things here, but you can't, right? It's just a set. But because of this bijection, you first move to the space where you can add, then you add, and then you come back to this. So this is how you can define addition here. And similarly, you can play the same game for scaling and make this into a vector space. All of this is very, very general. If you have some set with some structure, let me not use V. Suppose you have some set M with some structure. It could be a vector space if you know about other things like manifolds or, algebraic varieties or whatever that might be. If it is in bijection with some ordinary set, you can pull back all the extra decorations on this set to decorate this as such. What is a bijection doing? A bijection is just renaming things. The elements of S looked a certain way. The bijection is just renaming them. But after you rename, you find that there is some structure in the renamed world. So why can't you use the same structure by removing the masks? Right? Just by wearing masks, if you have some structure, removing the masks will not undo the structure, so to say. Whatever. I'm saying too much for too little. So that's what we are going to do. We have a bijection from the power set to this particular vector space. So now we can make this into a vector space, right? And the addition here was the symmetric difference there. Because what happened to the symmetric difference operation? It became addition here. So the symmetric difference is playing the role of addition. And the scaling is defined in the most natural way. If you have a set A, you scale it by 1, you get the set A back. If you scale it by 0, you get the empty set. Right? If this is a 1, you get A. If this is a 0, you get the empty set. So that is how we will define scaling. We are just pulling back the scaling on f2 to the x. Think about it. Okay, and that makes the power set a vector space over f2. And further, the dimension of this space will be mod x because the dimension of f2 to the x is mod x. This vector space structure is chosen for phi to become an isomorphism. It was chosen deliberately to just make phi an isomorphism. We have this map phi, right? We are just making this a linear isomorphism. Just like here, the map capital phi here in this abstract situation will become a linear isomorphism once you make S a vector space via this addition and the corresponding scaling. So we are making phi an isomorphism. The dimension of this is clearly mod x, hence the dimension of this guy is also mod x. Okay, so the power set of any non-empty set has a natural vector space structure, and if x is finite, its dimension is mod x. If x is not finite, well, then it's an infinite dimensional vector space, which we do not want to delve in. Okay, so now I think we can go back to our puzzle. Yes, I think this is the last thing I want to discuss. So the puzzle is, as we discussed, it's written over here for your convenience. And now once you know that you have to use linear algebra, try to think about it. Don't just read the solution. Okay, so here is the proof. Since dimension of power set, so yeah, so I have to say that. So we know, or even before that, let's say the set C is nothing but a1 up to an plus 1. And in fact, it will be better to work with f2 to the x rather than the power set. It's better that way. Notationally better only. Okay, so this is our set C. And since one more notation. So let's say Fi or Fk denotes the indicator of AK, which as we know is an element of this vector space. Okay. So since the dimension of f2 to the x, well, what is x here? X is just 1 up to n, which I'll write like this. Okay, so since the dimension of f2 to the n is n, we know that this list of vectors is linearly dependent. Right? This has to be a linearly dependent list of vectors because these are more than the dimension of the vector space in which they lie. And thus, there exist scalars in F2, not all 0, such that this is the 0 function. When I write 0, this is the 0 of this vector space, which is the 0 function, or this all 0 tuples if you like, but I'm thinking of everything here as functions. Maybe just to emphasize that, I will write 1 up to n here, although it's really the same thing. Rather than thinking of these as tuples, I'll think of them as functions. So we have that. Now, not all of them are 0. So whichever are non-zero you keep, others are anyway killed. What I'm saying is, if alpha 1 is 0, then alpha 1 f1 is 0. So those are anyway killed. So this is nothing but, you can write it maybe as follows. What's the best way to say it? Now, I just want to write this equation without writing the terms which are killed. So let's say alpha I1, alpha I2, up to alpha I k are non-zero, are equal to 1. Non-zero means equal to 1 because F2 has only 2 elements, are equal to 1, and others are 0. So from this equation star, the star becomes alpha I1 plus alpha I2. Sorry, what am I saying? Fi1 plus Fi2 plus dot 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 Fik. This is 0, where k is certainly non-negative. Sorry, k is in fact positive, because at least one of them is non-zero. If all of them were 0, then that is not a witness to the linear dependence of these functions. We already said that not all are 0, so k is certainly a positive integer. Okay, so we have that this is the case, and now we claim that the family S defined as has the required property. Right? To make things more clear, this equation is saying nothing but the following. It is just saying, by notation, it is saying, it looks ugly because so many subscripts, but what can I do? This is what that equation is saying. And we are just saying that if you make this as your subfamily, right, this is our subfamily, we are saying that every element of this guy lies in an even number of these people. So you fix some x in 1 up to n. We want to show that it lies in an even number of these guys. But that's very clear because this being 0 means what? It outputs 0 on every input. Which means once you feed x in it, this is 0 for all x. This is 0. Fix a particular x. The left side 0 implies that you see that how many of them give you a 1. You just record how many of them give you a 1. Whatever that number is, that number must be even because the output is 0. The ones which give you 0, well, they don't contribute. The only contribution can come from those places which output a 1 on a given x. Fix an x, just ask, will you give me a 1, will you give me a 1, will you give me a 1, and so on. Since ultimately you are getting a 0, there has to be an even number of them which output a 1. And those which output a 1 are precisely those for which the x is contained in the corresponding sets. So for any x, x has to be contained in an even number of these people for this equation to hold, because otherwise this equation will not hold, and that's it. So using linear algebra, even though I went over it in gory detail, using linear algebra, we immediately were even able to nail down what that set is. This is not so obvious using pure set theoretic arguments, even though the problem is purely set theoretic. Okay? And one more thing, since I'm assuming, or maybe I shouldn't, but maybe this is the first time you are seeing this kind of an argument, it will feel foreign, and that's okay. It will feel foreign, but very soon you'll get comfortable with it. So there was a teacher of mine at a certain institute I used to study in. He used to say that mathematics is hard, but very soon you get comfortable with it, and then you watch others suffer. And that is very true when you learn this kind of technology. Okay, this may seem hard at first, but just use it. Just use it. We will also see some more examples of it in the coming lectures. And yeah, you will get used to it, and then it will be second nature. Like this will be part and parcel of your arsenal of tools. All right, so with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.